Hello, space enthusiast.
You're now listening to Space Forward.
Join us as we talk to leading space scientists and engineers about humanity's potential to achieve a multi-planetary presence within our lifetime. I'm Hussein Bukhari.
And I'm Kelly Kowalski, your hosts.
Tune in now for episode 11, Finding Intelligent Life in the Cosmos with Professor Avi Loeb.
There was a report by the intelligence agencies in the US to Congress admitting that they're not doing their job. That's a very unusual admittance by the most conservative organization, which is the government, to say, we're getting paid to figure out what flies in the sky of the US. There are 143 incidents where we saw an object that appears to be real, but we don't know the nature of these objects, these unidentified aerial phenomena, UAP. And rather than scientists ridiculing the subject and shying away from it, I think that science has an obligation, and science can try and explain it.
Join us for part 2 of our interview with astrophysicist Avi Loeb. Find out about Breakthrough Starshot, a proposed flyby mission to our neighboring solar system, Alpha Centauri, and the Galileo Project, looking for signs of extraterrestrial technology the scientific way.
Get ready. We're going forward with Space Forward.
So Hussein, in your interview with Avi Loeb, you talk about this textbook, Life in the Cosmos, which he co-authored with Manasvi Lingam. And it's a pretty rigorous and scientific analysis of the many possibilities of life beyond our planet.
Yeah, he explains that it's an updated version of a textbook written in 1966 by a Soviet astronomer and astrophysicist by the name of Iosif Shklovsky. And it was later on translated into English by Carl Sagan. Essentially, the book is how to make the study of life elsewhere in the cosmos more mainstream.
So I guess in this updated textbook, Avi brings up something called the Kardashev Scale, a theoretical model that classifies how a potential intelligent alien civilization might harness different levels of energy.
Yeah, and the Kardashev Scale, it was developed in 1960s by a Russian astrophysicist. It measures the energy consumption of a civilization. But today, we're looking at the expenditure of entropy, which is the second law of thermodynamics and is also measuring wasted heat in a system. So we're looking at the expenditure of entropy by a civilization instead. And Avi, in his textbook, is referencing this as one way to measure technosignatures.
Cool. Let's go to the interview with Avi Loeb.
So I kind of want to go back to the book for a second. And you spend roughly 10% of the core content of your book on Kardashev Scale. Do you want to maybe give us an overview of what it means and why it might be significant?
Yeah, so the Kardashev scale refers to how much energy is being harvested by a technological civilization. And of course, the level that we are currently using is quite minimal. We're using a fraction of the sunlight that is intercepted by Earth. And you can imagine that in the future, we will use more of that. And eventually use all the energy or a significant fraction of the energy that is landing on continents, solar energy. That is sort of the beginner's level in the Kardashev scale. And you can imagine then surrounding the sun by photovoltaic cells that will use up much more energy than the surface area of the Earth, okay? And there is this concept of the Dyson sphere, which I must say, engineering-wise, is very challenging. It's difficult for me to see how easy it is to construct a sphere that will be stable around the sun. But at any event, the idea is that you can, in principle, use all the power coming off the sun or some significant fraction of it. And then, of course, you can imagine using the energy of the galaxy as a whole, many stars within the Milky Way galaxy. And you can even be more ambitious and say clusters of galaxies, like 1,000 galaxies. The more energy a civilization uses, of course, the more visible, the more easy it is for us to see it. Because if it modifies the energy output of a star, we can look at stars and see if there is any peculiar star where energy is being blocked artificially by a Dyson sphere. If energy is being used on the surface of one planet, it will be difficult for us to tell, except if that energy is being beamed, for example, in radio signals or in laser beams that we detect as flashes of light, which is possible. For example, just to give an example, there are these fast radio bursts. These are flashes of radio waves that last thousands of a second that can be seen all the way throughout the universe. And the popular belief now is that they are produced by neutron stars. These are stars that are the mass of the sun with a size of a city, about 12 kilometers in size, that if they have very strong magnetic fields can produce these flashes of radio waves. But we don't know for sure. Only in a few cases we have some potential evidence that it's indeed the emission from neutron stars.
So curious to hear your thoughts on this. That you mentioned that advanced civilization utilizing more energy, but shouldn't it be the other way around? The advanced civilizations would optimally be energy optimized, or at least they should be.
Yeah. So I don't subscribe to the Kardashev scale. I mean, what I said is that it's easier to detect if there was a civilization modifying the energy budget of its larger environment. It would be easier to tell that it's out there because we will see something unnatural out there. But frankly, I think that most likely the best you can hope for is a civilization taking advantage of the energy impacting on its planet, and beyond that, the civilization will venture into space. So for example, 100,000 years ago, we left the jungles of Africa. And now humans occupy apartment buildings in cities for their entire life. And it's a very different environment, living in an apartment building for your entire life compared to living in a jungle. That's a huge difference. And we managed to make that transition. So I can imagine that in less than 100,000 years from now, we will build a platform in space and occupy it. I see that less of a leap than the transition from a jungle to an apartment building in London. So if you think about it, once you go into space, well, first of all, you protect yourself from a single point catastrophe. It's just like the Gutenberg printing press that once it produced copies of the Bible that were previously handwritten, it was not such a disaster if one of them got damaged because there were many more. And in the same fashion, if you distribute humans on platforms in space, you won't worry too much if something bad, like climate change on Earth. Okay, so part of humanity will go extinct, but the rest will be out there on platforms. So as long as there is someone to carry the flame of human consciousness somewhere, and it could be also AI systems that travel through space, that do that. There is this biblical story in the Old Testament talking about Noah's Ark. Noah worried about the great flood, and he built an ark. By the way, the ark dimensions are described in the Old Testament, and they are just the size of Oumuamua, in how many meters and so forth. And the point is that we could think about Noah's spaceship, by which we have an AI system with 3D printers that could replicate life as we know it on Earth on other planets if we give it the DNA information, and as long as we can produce synthetic life. And people are trying to do that in the laboratory right now, starting from a soup of chemicals and making life out of it. And for example, I have a colleague at Harvard named Jack Szostak, and he is getting close to producing a living cell out of a soup of chemicals. And once we are able to do that, once we can produce life, we could potentially think about producing it elsewhere, on other planets, rather than carrying a whale or a bird or a lion on a spaceship along the lines of Noah's putting animals in the ark. We can actually carry just the information about their DNA and use the raw materials on other planets to make them there. And, it's just like the Gutenberg printing press. Once we produce things like we have on Earth, then at least we can rest assured that a single point catastrophe will not be so damaging. And I think that's one mission, that, the longevity of what we find precious here on Earth will depend on the way we venture into space. So my point is that I think long before we try to harvest all the energy from the sun, which I don't think will happen. So I think Dyson's idea, although fancy, is not real. Long before that, humans will go on platforms in space and just live life there happily with the amount of energy they have. Now, you ask yourself, is it really necessary for them to harvest much more? Well, one example where they might be ambitious is if they want to propel themselves to close to the speed of light so they can travel great distances over a short time. And that's exactly a calculation that we have done with my colleague Manasvi Lingam, who wrote the book with me, the textbook. We estimated that the kind of power that you see in fast radio bursts at a cosmological distance is the power required for a civilization to boost a light sail close to the speed of light for a big cargo that could include, in principle, people at a very low acceleration so that we can tolerate it. By the way, just to give you a sense, what we are now sitting on top of the Earth, right? So we feel an acceleration of 1g. That's the force of gravity keeping us on the surface, okay? And you hear about fighter pilots getting up to a few g and their body, it's not an easy experience. But at any event, if you imagine a spaceship that carries you with an acceleration of 1g, exactly as if you're sitting on top of the Earth, just exactly the same way. There is no distinction between the acceleration of gravity and the acceleration of a rocket. That's a realization that Albert Einstein, realized when he came up with the general theory of relativity, the theory of gravity. He had a thought experiment about an elevator that goes in free fall where gravity disappears because relative to the floor of the elevator, you're not accelerated at all. You are floating. So if you have a rocket pushing you at 1g, it would feel just like being on the surface of Earth. And if you have that rocket operating at 1g for a year, you would reach the speed of light.
Wow, it's kind of sad. In our lifetime, we won't be hopping on any spaceships and jetting around the universe.
Yeah, but there are ideas to send smaller uncrewed space probes to the next solar system over the Alpha Centauri system.
Yeah, that's right. You talked to Avi about that idea and pursuing it through the Breakthrough Starshot project, a project founded in 2016 by Yuri Milner, Mark Zuckerberg, and Stephen Hawking.
Definitely, we did. And the idea behind the project is to send some uncrewed space probes, very light ones, to the system. And in fact, in the other episode, we interview Zach Manchester, who's kind of the inventor of these chipsats. You can listen to our conversation. It's episode 8.
Okay, but before you go to episode 8, let's get back to Avi and find out how he got involved in the Breakthrough Starshot initiative.
In May 2015, a black limousine parked in front of the Center for Astrophysics at Harvard, and out of it came an entrepreneur from Silicon Valley named Yuri Milner, who came to my office, sat on the sofa in front of me, and asked me whether I'm willing to lead a project that will design a spacecraft that will visit the nearest star within his lifetime. And that meant, since he is the same age as I am, that meant within a couple of decades. And I immediately calculated that since the distance to the nearest star is 4 light years, you need the spacecraft moving at the fifth of the speed of light. That's 1,000 times faster than the chemical rockets we've been using so far. And a factor of 1,000 is a lot. It's roughly the factor of improvement between Ford's T-car, the first car that was used, the first automobile, and Sputnik, or all the spacecrafts we designed. That's a factor of 1,000 between them and the first car. So altogether, we are talking about a huge leap in speed. And I told him that I have to think about it, and then came up with a concept of using a light sail, basically pushing it with a very powerful laser. If you have a thin film of material, roughly the size of a person that weighs about a gram, and you shine a powerful laser on it with 100 gigawatt over a few minutes, then it will reach a fifth of the speed of light. And it will traverse a distance that is 5 times the distance to the moon during that time. And that was the concept of Starshot, that the initiative that I proposed to Yuri as the only path forward to reach those speeds. And we're currently working on critical elements of this technology. They include the design of the laser beam, how to combine a lot of small lasers into a very powerful laser beam, the design of the sail itself, making it of materials that reflect all the light, because we don't want the material to absorb more than 1 part in 100,000 of the light, otherwise it will burn up. And it also needs to be very sturdy, very strong, the material. And then the final thing is the communication across a distance of 4 light years. It's a non-trivial problem how to send back information to Earth. And imagine taking a photograph of the habitable planet around the nearest star, Proxima Centauri. What we would like is to get that signal across 4 light years. That's a challenge that we are also working on. So at the moment, I would say it's work in progress. We're trying to look into these challenges, and we haven't yet gotten to the stage where we build a system to demonstrate that it works.
So based on that, I'm sure one of the critical elements is getting there, but the other critical element is how to decelerate as you get to Proxima B.
Okay, it's not possible if you move at the fifth of the speed of light. If the spacecraft moves at that speed, it's not possible to slow it down, because what you need is a laser system similar to the one we use to launch it, to slow it down over there. And just the starlight is not sufficient to slow it down. So it will just pass through the system. And if you want to design a system that can maneuver and slow down, then it needs to move slower than that speed. And of course, that can happen, but it would take more time to get there. If you were to use chemical rockets to get to Proxima Centauri, it would take about 50,000 years. So we should have sent it when the first humans left Africa for it to be there by now.
Yeah, about now. Yeah, that'd be fair. Is there a goal associated with this project where, getting to Proxima B and taking a picture? I mean, how do you take a picture at the speed that you're going at?
That's not an issue, actually. It turns out that there will not be much distortion of the image as a result of the high speed. I actually wrote a paper about that, and there is plenty of time to take the image when you pass near the planet. So it will just look like an image. Even if you were to move close to the speed of light, it turns out that an object that is, let's say, circular in reality would still stay circular, even if you move close to the speed of light, despite of what you might think that, according to Einstein's theory of relativity, it should get squished. But it turns out that it's not. If you do the calculation that, in fact, a circular source would look circular to a camera moving close to the speed of light. And one simple way to think about it, that, after doing the calculation, I realized, the speed of light is constant in all frames of reference. That was Einstein's insight or assumption. Given that the speed of light is constant, then even if you're moving very fast relative to the source, light from the circular edges of the source will travel to you at the same speed. You will still see it circular, and it will not be squished. It's just tilted. So if there are any features on the source, they are tilted relative to their real orientation.
Taking a photo of an exoplanet.
So now you can see why Avi looked into the possibility of the interstellar object Oumuamua being a potential space probe flyby.
Yeah, I can see why he would pose that question, but do you think Avi might have a bit of confirmation bias in that he was the guy helping to design a light sail probe to Alpha Centauri?
To be able to pursue a destination like Alpha Centauri, you need to have a passion for technology. So I think he's biased based on what he's worked on thus far.
You also brought up in your interview one of my favorite quotes by Arthur C. Clarke. Any sufficiently advanced technology is indistinguishable from magic.
But there's another guy who put a twist on it.
Yeah, another science fiction author, Carl Schroeder, rephrased Clarke's quote and said, "Any sufficiently advanced technology is indistinguishable from nature." Basically, he's pushing the notion that either advanced civilizations don't exist or we can't see them because they're not that different from nature.
So in a sense, looking for technosignatures might be a lost cause if aliens are super intelligent and they're able to blend in with nature.
Yeah, I asked him about Schroeder's quote. If it's true, would we be able to see a natural-looking alien technology?
Well, let me give you a simple example. Suppose the next object that looks as weird as Oumuamua is discovered a year in advance before it approaches us by the Vera Rubin Observatory that will start operations in 2 years. It will be much more sensitive than the Pan-STARRS telescope that discovered Oumuamua. And therefore, it could see things to greater distance or find more of the same. And suppose we have that information, then we can send a spacecraft equipped with a camera that will come close to it, just like OSIRIS-REx mission got close to the asteroid Bennu and actually landed on it and will bring a sample back to Earth. So now, if we get close to an object, we take a photograph and we see screws and bolts on the surface, and we see some buttons on the surface, and we see a label saying made on exoplanet X, then I don't think it's a rock. That's an easy thing. So when you say indistinguishable from nature, it's clearly distinguishable because what we sent out, Voyager or New Horizons, is clearly distinguishable from nature. If you look at the molecules that our refrigerating systems produce in the atmosphere, CFCs, they're clearly distinguishable from nature. You don't produce such molecules that destroy the ozone layer naturally. You just produce them by industries. And there is no doubt about it that if you detect CFCs in the atmospheres of other planets, it must be industrial pollution, okay? So we can search for that. There are markers of a technological development that cannot be mimicked by nature because the chance of that happening randomly is similar to the chance of a monkey typing Shakespeare's work on a typewriter. It's very small. I mean, obviously the monkey might be lucky, but you can ask what's the chance that the monkey would type Hamlet? If we see Hamlet coming out, it's not a monkey. It's Shakespeare. Okay, so so my point is we should be able to tell. The astronomy community is currently defining the next generation of telescopes that it wants to use. And one of the motivations for the next spectrograph that on a big telescope that we will use would be to detect oxygen or methane, the kind of gases that we associate with life on Earth. To detect them in the atmospheres of planets around other stars when they transit the star. And the problem I have is, that the Earth did not have much oxygen in its atmosphere in the first 2 billion years for about half of its life. And even though there were microbes, it's not fully understood why just after 2 billion years, the level of oxygen rose so rapidly. But at any event, that's a fact. Therefore, if you don't find oxygen on a planet like the Earth, it doesn't mean that there are no microbes. But if you do find oxygen, it could also be produced by natural processes, some chemical reactions that produce oxygen. So it will never be conclusive. And yet, the astronomy community is coming up with proposals for telescopes that will cost billions of dollars. And my point is, if we detect CFCs, these industrial pollution molecules that cannot be produced by nature, then we will know that not only there is life, but there is industrial life, intelligent life out there. And with the same spectrographs, we can search for those. And so, that's one interesting way of looking for intelligent life. Another one is to look for artificial lights. We just wrote a paper with an undergraduate student at Stanford saying that the James Webb Space Telescope can search for city lights on the dark side of the habitable planet next to the nearest star, Proxima Centauri. You can infer whether the dark side is completely dark or it has some city lights on it. So that's another interesting signature, looking for artificial lights. One can also look for artificial lights in the solar system. Well, how can you tell if you see a source of light? How can you tell if it reflects sunlight or produces its own light? The way you can tell is by how it dims as it gets away from us. A source that just reflects sunlight, like asteroids or rocks, the amount of light that we see, the flux that we see, the brightness of the source declines inversely with distance to the fourth power, because as the source moves away, it intercepts less light from the sun, and then because it moves farther away, we see even less than that. So altogether, it gives you a dependence on 1 over the distance to the fourth power. Whereas if a source produces its own light, like a spaceship or a city, then you would see an inverse distance squared dependence. So that's one way to tell the difference. And we show that a city like Tokyo, for example, would be visible all the way to the Kuiper belt, the edge of where the planets are in the solar system. And I asked, after we wrote this paper, I asked an astronomer that discovered most of the objects in the Kuiper belt, and I said, did you ever check if their flux, the brightness, declines inversely with distance squared or distance to the fourth power? And he said, why should I check? It must be rocks, therefore it must go like inversely with distance to the fourth. And that shows you that, without checking, without being open-minded, you will never discover new things. So I'm trying to change this intellectual landscape.
So why don't you tell us about how you're trying to change the landscape of searching for intelligent life?
Yeah, so SETI was engaged for 70 years, mostly in the search for electromagnetic signals, for radio signals or laser signals from distant civilizations. And that is just like trying to have a phone conversation. You need the counterpart to be alive when you're listening. And it may be misguided because it's possible that most civilizations predated us and they are dead by now. In that case, it doesn't mean that we cannot find their relics. We can just engage in archaeology, just like we do on Earth, where we find relics left behind from cultures that predated us. And we can do the same thing in space. And so my point is, looking for physical objects is a completely new frontier that was not yet practiced. And Oumuamua was a wake-up call.
So on that note, why don't you tell us about the Galileo Project?
Right. So we have two major components to the project. And I should say this project was conceived over the past month, partly as a result of my book about Oumuamua. The book is Extraterrestrial, and there was a huge response and interest from the public. And the second part is a month ago, there was a report by the intelligence agencies in the US to Congress admitting that they're not doing their job. That's a very unusual admittance by the most conservative organization that you find, which is the government, to say, we're getting paid to figure out what flies in the sky of the US. There are 143 incidents where we saw an object that appears to be real, as far as we can tell, because we detected it in multiple instruments and various eyewitness testimonies that noticed the same thing, doing the same thing. But we don't know the nature of these objects. And that, for the intelligence agencies to admit that, I find it quite unusual, because that's their job. And secondly, if they thought that it's China or Russia, then they would have kept it to themselves. They wouldn't come to the Congress and say, something that we believe is human-made, we don't know the nature of. Because, if it's China or Russia, they really need to figure out what technologies those nations use. But if they believe that it behaved in ways that cannot be explained by human-made technologies, then of course they would report about it. So my point is, after this report came out, I made the point that, it's sufficiently intriguing for this subject to move away from the talking points of politicians and military personnel to the realm of science, because scientists have an obligation to attend to the interest of the public, in particular politicians, that say, here is something we don't understand. And science can try and explain it, rather than scientists ridiculing the subject and shying away from it. And by that, they would maintain the uncertainty about the nature of these objects, these unidentified aerial phenomena, UAP. You know, the analogy I would draw is 1,000 years ago when some people argue that the human body has a soul and therefore anatomy should be forbidden. So just imagine that scientists would say, okay, this subject is controversial, there is nonsense being said about it, we don't want to deal with it. Where would modern medicine be if we didn't operate people and we didn't know what's inside the human body? So I think that science has an obligation to attend to a challenge posed by the government, where the government says, this is something we don't understand. You won't expect a politician to explain what is being seen in the sky. That's the job of an astronomer. And so I said, well, indeed, scientists should do it. And around the same time, the administrator of NASA, Bill Nelson, said the same thing. So I actually wrote to people under him and said, here I am to serve. If you want, I'll be glad to help you. I didn't get a response. And then a week later, I get an email from the administrator of the astronomy department at Harvard and telling me, you have a new research fund. And I said, what do you mean I have a new research fund? That never happens in academia. Who is the person that gave me that money? And she said, I'm not sure. Let me look into that. And it took them a day to get back to me. But then a multi-billionaire showed up on the porch of my home and asked me questions about my book. And then another multi-billionaire came over, and altogether within 2 weeks, I had nearly $2 million. And at that point I said, okay, that's enough. I don't need anyone's approval. I can assemble a team of exceptional scientists, mostly astronomers, that will design telescopes that could tell us the nature of UAP. And the way to do it is by having in each system a few telescopes that get a high-resolution image of an object of interest, so that we can tell that it's not a bird, it's not a drone, it's not an airplane, it's something else. And then monitoring the motion of this thing in 3 dimensions. And the data will go to a video camera that will feed it to a computer system that will analyze it. And just in a scientific way, you don't want to rely on a camera that is in a jittery cockpit of a fighter jet, because that's not under control. And eyewitness testimonies are not relevant in science. You can't write a paper saying, this person told me that. This is not acceptable in science. You have to rely on instruments giving you quantitative data. So we will do just that, design a telescope system that is optimal for the purpose that we are talking about. And then the more funding we have, the more telescope systems we will build. Then in principle, they can go to many geographical locations, many countries. And that's what we hope to do. I mean, I hope to have hundreds of those or even more. So that hopefully will provide open data. And then I think the public could potentially look at this data and analyze it on its own, because it will be open, the analysis will be transparent. I don't want to look at classified data because it would limit my freedom as a scientist. And frankly, much of this data was taken by instruments that were not optimally designed for this purpose. So I think in terms of the public, the most interesting aspect would be the open data that we will release, because we are designing the telescopes to be not just the kind of things that you can put together yourself. I mean, it will be professional telescope systems that astronomers design, but the data from those would be available to everyone. And once we get to getting the data, it will be open to the public, and the public might identify things in the data that we haven't noticed. And that would be fascinating. So it's very different from the data collected by the government, by classified sensors. So we don't want to deal with government-owned data. We want to produce our own data. Just like a kid, when you tell a kid what the truth is, the kid ignores you. The kid wants to find out the truth himself or herself. And that's what we are doing in the Galileo Project.
I mean, I'm definitely very, very excited to see if our audience and when our audience is ready to engage with you on this Galileo project, because I think it's taking that next step to go in that direction, because science requires valuable truth and we need to extrapolate that as much as possible. So thank you so much for being on here. We really, really appreciate your time. And we hope we can have you in the future again.
Yeah, it was my pleasure. And I'll definitely be glad to report about results that we find. Because, we should keep our eyes on the ball. And if we ever get the ball into the net, I will let you know.
Keep your eye on the ball.
Spaceballs. Wasn't that a film? Do you know about that one?
No, I don't.
Oh, it's a super cheesy 80s film.
I need to watch it with Mel Brooks and John Candy.
Okay. Either way, I'm pretty excited to hear if Avi ever finds those space balls or space orbs or spaceships. So let's stay tuned for that.
Thanks for joining us for another episode of Space Forward. Stay tuned for more deep dives, explorations, and journeys we have in store for you. Follow us on Spotify, subscribe on Apple Podcast or YouTube.